Hey everyone, so this is the second part in the cross entropy loss video. So the first part is already uploaded and this is the second part. In the last part we covered ignore index and reduction. These were the two parameters we covered in cross entropy loss. I told you that size average and the other one reduce has been deprecated, so we will not be discussing that because that is already included in reduction. Today's agenda is to understand weight, okay, and label smoothing, right? So let's first start with weight. What is weight and why it is none? So weight is basically, if you go and see over here, it says it's a manual rescaling weight given to each class. Important part is given to each class, which means given to each neuron. We will draw the diagram and we will see. Okay, if given, it has to be a tensor of size C and floating point type D type. Okay, that is not very important. What is important is, let's say that you have a neural network. Okay, so there are intermediate layers, and then final layer, let's say there are let's say 1 2 3 4 5, and let's have 5 1 2 3 4 and 5. So there are 10 neurons at the end. Okay, so this is your configuration. So obviously what will be the output here? O of 0, there will be O of 1, and same like this you will have O of 9, right? So for one example, so if there is one example, you are going to have out of let's say 1, and it's going to be O0, O1 up to O9. So for one example there are these 10 values. What if there are n examples? So it will be n cross whatever the size whatever the number of neurons are there in the first layer. So let's say there is 1 2 3 4 5 6, so n cross 6. So in first example it was 1 cross 6, and if there are n examples, then we will have n cross 6. Okay, so how many do you expect? Obviously for one example you will have one output of the last layer, so for n you will have n output. So you can say O of 2, O of out of 2, out of 3, up to out of n. Why? Because there are n examples, and each of these out will have again O1, O0, O1 up to O9, and so on and so forth. So can we say, and the last one is also going to have similarly O1, O0, O1 up to O9. So if you try to put it in a form of a matrix, what you will have, because this is very important, this is what we'll be using in our example, so listen very carefully. Okay, so out of 1 is here, it was O0, O1 and up to O9. Okay, let's just put this also index so that we don't get confused. So it is O of 10, O of 11 up to O of 19. So out of 2 will be O of 20, O of 21 up to O of 29. And similarly you will have n out of n. Let me go till here. You will have O of n0, O of n1 up to O of n9. Okay, so what is the dimension of this? This is n cross 10. Why 10? Because it starts from 0 and goes till 9, so it is 10. Now I hope you have understood this. Okay, now what it says is, this one says we need to weight says it is the manual rescaling. It says the manual rescaling of individual classes. Individual classes. Now my problem is, or let's say classes, my question is, what does this mean? It means that then in out of these 10 neurons, because these 10 neurons represent 10 classes, so you say if I say over here weight of 3, let's say class 3 is equal to 2 and weight of class 7 equal to 4. What this means is, so let's say this is the class number, which means index is 3 minus 1, that's 2. So this is first neuron, 0th neuron, first neuron, second neuron. It says the weight of this is 2, and for the 7th neuron, which is 7 minus 1, that is equals to 6. So index 6. So let's start with index 0 1 2 3 4 5 and 6. For this one the weight equal to 4. What this means is this output here will be twice as important as this. And same thing you can write for, let's say you can write here 3, you can write here let's say 6. You can write here something 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 something. So you can write some values over here. These are the weight, you see, a weighted average or weighted mean. This is basically the weightage of a particular class. Now where that weightage will be used, obviously it will be used in the loss function, which means that if this is the correct one, this is the neuron is let's say the highest is let's say 6. Okay, if this is the correct neuron, it has so much of value, which means that if this is misclassified, listen to me very carefully, if this is misclassified, the error is going to be high. I hope you understood this. Now let's go to a concrete example and see how this applies. Okay, so we just have to run this one, and then we will so this is import torch and torch.nn, and then we can slide down, because these are the things we have already covered in the last, and it is not important to know at this point of time. Okay, because these parameters generally speaking are not very related. Now as we are dealing with weights, I have explained to you what is out. 9 cross 10. 9 is what? Number of examples. 10 is what? 10 neurons at the end. Okay, so here what I basically mean is, here n is equal to 9. So n equal to 9. So input becomes 9 cross 6 and output becomes, this n is 9 cross 10. So this is your out. Okay, this is what is denoted over here. So basically we are taking random numbers. Why? Because we don't care about the actual, because we are not training any model, we are just taking an example to understand. Okay, now what is this? Now this function is I think the video is already there. I have okay, if it is not there, I'll be uploading videos regarding these type of torch functions which are not under the NN, that is neural network module, but don't worry, it will be there. Okay, so what this torch.multinomial does, now what it does is, I'll just explain you with a diagram so you will understand. It says, first give me torch dot ones, you can have anything over here, torch dot ones, let's say of 10, which means there are 10 values. So it's like 1 2 3 4 5, 1 2 3 4 and 5. Okay, so there are 10 ones over here. Okay, so it can also happen that this is 2, which means that its probability is higher, but again just assume this is a uniform distribution. Okay, this basically represents probabilities. Now you can say, oh, why this does not sum up to 1. Obviously you will normalize it. I have not normalized it, so don't worry, but this you can say is a uniform distribution over here. It represents, right? So this is what it does. Now this 9 is basically take out sample 9 times from this distribution, which means, let's say example, this this could be a distribution which is not normal or which is not uniform. It could be 2, it could be 1, it could be 3, and all. Okay, but we are taking a uniform distribution and we are saying sample 9 times out of this. Okay, so sample, let's say you can, this is a 0, this is 1. I'm talking about the index 2 3 4 5 6 7 8 and 9. So let's say you have to sample, let's say 3 times. So since this is a uniform distribution, all of them have equal probability. So let's say you took out 4, so your output will be 4 in the first. Okay, you have to take 2 more. Let's say this time you took out 8. Okay, and third one, let's say you took out again 8. Okay, why again 8? Because we have said replacement equal to true, which means once you take out a particular number, it can be taken out, or it can be chosen, or not taken out, it can be chosen any number of times. This is what is basically replacement equal to true. Okay, so I hope I was able to explain to you. We are not taking ones, we are taking indices. Okay, 0 1 2 3 4 5 6 7 8 9, these are indices, these are not ones. So you don't expect like this 3 ones. No, you are taking indices. Right now this is run already, so let's try to print out and see what is happening over here. So this is first output. So these are 10 numbers. Okay, 1 2, this is 3, this is 4 5 6 7 8 9 and 10. So basically these are the, like, you can say this is the output of the first example. Okay, this is the output of the second example, this here is the output of the third example and fourth example, and so on and so forth. So which is, this one is the output of the ninth example. Okay, so these are the unnormalized logits that come out from the last layer of the neural network, basically from this layer. Okay, this particular layer. Okay, all of the neurons over here. Now, what are ins? Ins are basically indices that we have seen over here. We took out some indices, right? We took out 488. So these are indices over here. These are what I am going to say as correct indices. Since we gave 9 examples, there are 9 total numbers over here. So in the first example, the first index was correct. First index first, which means index starts from 0. So which means second class was correct. Here, fourth class was correct. Here, 5 plus 1, sixth class was correct. Here, 3 plus 1 fourth class was correct, and so on and so forth. Okay, so you'll not see a 10 over here because their index is from 0 to 9. Okay, this basically means, now how I am going to assign weight. I told you about weight, right? I told you about weight over here. It is rescaling of individual classes. I am saying over here that let all my classes initially again have a uniform distribution, that is torch.1's uniform distribution. However, what I am doing here is I am going to increase the weight of all the even values. So you can see over here, let's put it over here just to see what torch.arrange into 2 does. Okay, so first let's see what torch.arrange does. It will basically give you values between 0 to that particular value that is there inside the bracket. However, that particular value inside the bracket will not be included, which is 0 to 4. Okay, what if you multiply this by 2? Obviously all these numbers will be multiplied by 2 and you will get 0, 2. So it was all 0, 1, 2, 3, 4. If you multiply all of them by 2, you get 0, 2, 4, 6, 8. I am saying whatever weight is there at these indices, which is 0, 2, 4, 6 and 8, multiply that by 2 and save it back. So here what you will have is you will have this the first one is a 0, right? So this one is 0. See, it is multiplied by 2. Again, this one is 1, position 1. So 1 is not in this here, so it will remain as 1. Now position 2 is there, yes. So similarly you can see all the even positions. So you can see over here all the even positions have been weighted, have their weight increased. See, 0th position is 2, second position is 2, fourth position in 2 is 2, and so on and so forth, and rest everything is 1, which means you don't have to pass any. So this is our weight. You don't have to pass any probability distribution. All these sum, all these will sum to obviously greater than 1, but we don't care because at the end of so I am assuming you are familiar with the softmax cross entropy theory, and the weights will be normalized, right? So don't have to worry. You can also check it here. Even you can go and check it over here. See over here, when you talk about the loss, it says divided by the summation of W of n, where again we have assumed there are no ignore indices. Okay, so weight of n is basically this 2, 1 and all those things. Okay, now let's try to figure out the cross entropy loss. Okay, so this is our general cross entropy loss, which does not have weights included. Okay, you can see it is all the weights. That this loss has been found by using this particular formula where there are no weights. So all of this weight is equal to 1. Okay, so this does not matter, and this is an ignore index is also there are none, which means all of this will just reduce to log of this expression, because weight again is all 1, so you don't have to care. And here also all of them is, there are no ignore indices, so we don't have to care. Okay, now let's get back. So you can see these are our since reduction equal to none, we can see the entire vector over here. These are our losses. So this is the loss for the first example, this is the loss for the second example, this is the loss for the third example, 4th, 5th, 6th, 7th, 8th and 9th. This is the loss for the last example. Okay, now what I'm going to do is I'm going to put weight, the weight equal to weight, and then rest everything is copied from here itself. Okay, reduction equal to none, out, ends, all of that is copied. Now let's see what happens. Now see, first of all, how do I understand this? You can see some of the places, like for example this 1.9823 remains as 1.9823. You see over here 1.6719 remains as 1.6719. However, if you see over here 2.0265 becomes into 2 4.0529. Why does that happen? Again you can see over here same example, 0.9453 has been multiplied by 2 and this has come. However, this still remains as 3.4813 only. Now how do you know? You see over here, wherever there is an even index, remember we took the even index and multiplied as 4. Wherever there is an even index, 4, 2, 8, 2 over here. Okay, so remember this is first, second, third, fourth, fifth number over here, sixth number, seventh number, ninth number. Okay, so fifth, sixth, seventh, and ninth. Since these are even numbers, they will be multiplied by 2. Their loss will be multiplied by 2. Why? Because the weight here is multiplied by 2. And you will see the same thing here. You will see fifth one, 1, 2, 3, 4, and 5. See, fifth one is this one, right? It has been multiplied by 2. Sixth is this one over here. It has been multiplied by 2. You will see seventh is here. It is multiplied by 2. And the ninth one is here. It has been multiplied by 2. Rest everything remains same. So I hope you get the logic of weight. Okay. Now let's go to something called as label smoothing. Now label smoothing is something that is not very hard to understand, and it's actually very intuitive if you understand. But the thing is that practically I haven't seen it to become very popular, because most of the times it does not give any substantial increase in the accuracy. Otherwise this would have been a very famous thing. It is there because in some cases, yeah, why it is there? Because in some cases it does work. However, in most of the cases it doesn't, or it does not give that much of an increase in accuracy, and that's why we mostly do not use it. Okay, but let me just go through for the sake of going through, and not only for the sake of going through, but basically explaining it to you. Okay, so what is label smoothing? It's a float between 0 and 1. It specifies the amount of smoothing when computing the loss. Okay, where 0.00 means no smoothing, which is basically your vanilla cross entropy. The target becomes a mixture of the original ground truth and a uniform distribution described in this particular paper, which we will understand over here. Obviously we don't need to get into the paper. In fact, we don't even need to get over here. I'll just explain it here itself. So whenever you talk about an example, let's say this neural network itself, let's say I'll quickly draw one simple neural network. So let's say this was your neural network. Okay, all these are connected over here, these are also connected over here. Now whenever you pass an example over here, okay, example over here, you get how many? 1, 2, 3, 4, 5 neurons. So you will get 5 different. So this will get O0, this will become O1, this will become O2, this will become O3, and this will become O4. So you will get 5 particular values: O0, O1, O2, O3, and O4. Now whenever you say, okay, this particular neuron is correct, which is O3 is correct, the third index, so we say 0, 0, 0, 1, 0. This is, what is this called? This is called one hot encoding. It's called one hot encoding, right? Everything is 0, and only where the class is correct we write a 1. Now in label smoothing, what happens? You say, why when you say 1 and you say all of it is 0, it means it is so confident. Let's say we have to, let's say there is a classifier which is let's say humans versus let's say dogs. Okay, let's say humans versus dogs. Obviously when you give a picture of a human being and then you say equal to 1, it seems as if you're so confident that this person with the image can never be classified as a dog. Now generally you can say, but if a person is in some kind of like something like this, he is not standing upright, he is on his legs, and the photo is actually half, and the person, this can also look like a person, as if this is the entire person is over here, but the photo, let me draw it again. So let's say the person is there, he's crawling on the floor, let's say, and his body, this dotted line is the body over here, this is the whole body, but the image that you took is only till here, is only till, let's say, here. The image that you took is only till here. Now the question I want to ask you is, even though we know a human eye can say and see this as a human being, doesn't it look more closer to a dog? Because the human being here is crawling, and generally in human photos humans are not crawling. So how can somebody, okay, a human being can say, but how to explain to a neural network that this is human by 1, even though there are some characteristics? See over here, only 2 things are there, it can say, okay, 2 legs are there, or even if there are 4, doesn't matter. Why? Because even obviously dogs have 4 legs, but I've just tried to give an example over here. Okay, I am saying the orientation of a person, and trust me, there are times where even humans get confused. So the idea is, when you say 1, it means you are 100% sure. In life, even humans are generally speaking not 100% sure. What this explains here, what this shows here, is too much overconfidence. That is all I wanted to say. This is the idea of overconfidence. When you say this is a human being, it's like only this is a human being, rest everything is not a human being. No, generally speaking, you are never that confident, okay? Because there are so many places where even people confuse whether this is a human being. You might have seen a photo of in a lake there is a monster. Actually, it's a log. It's a basically a wooden log that is there, but people say it's a monster. Same thing like that. And what I'm trying to mean is that humans even get confused, okay? So the idea is you should never give 100% answer to anything, even in real life, okay? Because there's always a sliver of doubt. Now what do we do to counter this? Obviously, what we do is basically label balancing. We say we take some probability mass from here, okay? The formula that we use is 1 minus alpha, okay, into 1 hot encoding plus alpha by k is the number of classes, okay? K is the number of classes, and alpha is a hyperparameter that can parameter that we tune. Basically, it's a hyperparameter that we tune. Now it is not a learned hyperparameter, so we define it before the training of the model, which is basically your label smoothing. This is a float, okay? So this can range, this alpha has to be less than 1.0, okay? I mean, I think it's 1 point, okay, both are included, so it has to be less than equal to 1.0. Obviously this cannot go more than 0. So what happens is, over here, the example will explain to you. So we are talking about label smoothing, okay? So again, what is torch.zeros of 10? It will give you 10 zeros. I'm saying at the second position I want 1. So if you do that, you have already seen it over here, all of them 0, but here I said on the second position I want second index I want 1. So here second index I want 1. Alpha I've already explained you what is it. It's a hyperparameter which is basically your label smoothing. I could have written here label smoothing also, but does not matter because in the paper it says alpha, okay? So formula I had explained to you, 1 minus alpha, you can see 1 minus alpha into OHE, which is this particular vector, plus alpha divided by number of classes, which is 10. Okay, number of classes, not number of examples. Examples can be anything. Number of classes, the neurons will not change. Can you see here, earlier we had all the elements as 0 and the correct index as 1, but you can see over here some of the all of the other elements, even the wrong classes have been given certain weight, which is alpha divided by 10. Okay, so alpha was 0.2, divided by 10 is 0.02, so alpha divided by 0.02 is given to all the wrong weights. And what is your OHE, which is the correct weight? What is the weight of the correct weight? It is basically 1 minus alpha, that is 0.8. So 1 minus alpha is 0.2, so 1 minus alpha is 0.8, and the addition of this one over here, so that is 0.82. okay, now obviously this should sum to 1, that is all I'm saying. So if you come over here, you will see the tensor is equal to 1.0. okay, now how does it apply? Again, let's assume that this is 0.1 label smoothing, which is basically alpha, but here you say label smoothing is equal to 0.1. In our example we took 0.2, and here we have taken 0.1. What I am saying is that the losses will not change drastically. Okay, so here you see 1.9823, again here also close to 1.9823, 2.03. okay, so it is close, actually very close. You can see if not this one, this is the scaled weight, right? 2.5859, it will be somewhere close only, 2.6343. so it has increased the weight and decreased the weight accordingly. So if you have any questions, please write it in the comment section. Thank you very much, and if you really like the video, please like and subscribe. Thank you very much, and bye.